Okay, so we're going to look at some more polymers, and it's quite important to be able to look at a section of polymer and then decide what are the monomers that that's made from. So let's have a look at this one, and I've made it easy by color coding it. But you can probably see that the two monomers there are going to be well, this black one is the dicarboxylic acid, or it could be the diacyl chloride. I've drawn the carboxylic acid there, could be the acyl chloride. So it's benzene 1,4-dicarboxylic acid, and the other one would be the diaminobutane. You've got 4 carbons there. And it's forming an amide linkage. So yeah, you're going to lose that at the end of each one, and you form the polymer there. Okay. Just while we are doing this, let's just talk about these polyamides. They can be broken down. They are biodegradable, because what can happen is they can undergo hydrolysis. So if I've got a water molecule here, got lone pair in the water, you have this bond is polar. You've got delta positive on that carbon. You've got two electronegative elements around it. So that means you can get nucleophilic attack by the water there, and you can hydrolyze it. So I don't think they're broken down particularly quickly in nature, but they are said to be biodegradable. Okay. Whereas if you look at a section of polymer from an addition polymer, so let's just have polyethylene, for example. All you've got there is you've got a load of carbon-carbon bonds. There's no polarity there at all, so they're not susceptible to attack by water molecules, by nucleophiles. So these addition polymers are not biodegradable. And that question comes up quite regularly. Why are polyesters and polyamides, why are they biodegradable, whereas the addition polymers are less so? Okay, so let's have a look at another polymer. Right, now this one you should be able to recognize is not a polyamide but a polyester, and the two the monomers are, well, you've got the blue one there, which is a dicarboxylic acid, propandioic acid, and you've got the diol, the ethanol, the ethane 1,2-diol. So they're the two monomers there. So it's pretty important to be able to recognize the monomers that they come from. They quite often ask you to do that. It's pretty important to be able to draw the repeating unit as well. So let's start off our square bracket there, and then we mustn't repeat anything, but we must include everything. So keep going, keep going, keep going. We should stop there. That's a repeating unit. And let's have a look at the amide that we did earlier. So if we start our bracket there, and we keep going to there, and we put the bracket in there. Okay, I don't think I've said before, but let's just say also, what is the amide linkage? Well, the amide linkage is that bit there. And in this one, the ester linkage is that bit there. Okay, so practicing drawing these is about the only way to really get it fixed in your head. Right, now let's have a look at something a bit different. You can see here we've got a section of a polymer there. It's a polyester, and I've drawn one in green and one in yellow, but you can see, unlike the previous cases where you have got two different monomers, this is just made up from one monomer. And if you see what this monomer would be, it would be, we've got a carboxylic acid, and you've got 3 carbons long, and you've got an OH at that end. So what's happening here with these is you've only got one monomer, and they're going kind of, this is the tail, and this is the head, if you like, and they're going head to tail, so that would form a polymer there. Okay, so we've got another molecule there. You get the ester linkage forming here. Remove that water there, and they can form a polymer. With these sort of monomers as well, what they can do is the head can kind of swallow its own tail, and it can form a cyclic ester. Okay, it can form a cyclic ester. So let's just draw that. It could react with itself. So if we have got 3 carbons, got the oxygen there. Okay, so that would be quite a. Okay, so that's this OH here, the carboxylic acid has reacted with the alcohol at the other end, and you can form a cyclic ester. Or what could happen is you could get 2 of them forming a cyclic ester. They've asked that. So if they said you get a cyclic ester with a molecular weight, the MR, I don't know what the molecular weight of that is, but they get a molecular weight which is bigger than that. So, and it turned out that it was when you've got 2 of them together. So you've got that there, and I'll draw this in a different color. So this forms a same monomer, different molecule, the green one. Okay, so that's going to have 3 carbons there. So 1, 2, 3, and the oxygen there. So that would be CH2. Okay, so you could also form that cyclic ester, which is going to have a bigger MR than that one. Okay, so just one other thing. They have asked a few years ago about, they had a copolymer, and the copolymer is when, right, let's say you had 6,6 nylon. Okay, so 6,6 nylon has got it's got 6 carbons long, which I'll draw them all in. You'll see why in a minute. 1, 2, 3, 4, 5, and 6. Okay, and you've got diaminohexane, 6 of them. Okay, so that's a section of the polymer, but these are just normal. Okay, that's normal hexane dioic acid. But what you can also do is every now and again you could include in there a different one. So instead of it just being, you have a branch coming off it and then a CH2 there. Okay, so that would be CH. 1, 2, 3, 4, 5, and 6. Okay, so it's a copolymer because most of the time you just have simply the hexane dioic acid. But every now and again you have one of these which has got this branch on it. Okay, I'll just put the hydrogens on there in a minute. And what this means, what this can do is, every now and again, if you get another polymer here, so this is another one with a branch coming off it, I'll draw in a different color. You've got CH2 here. Okay, so this is another polymer chain in purple. I'll just draw it like that. So what can happen here is you can basically form like the way addition polymers form here. You can break that double bond, and form a new bond between those 2. So effectively what you've done is you covalently linked 2 polymer chains. 2 different polymer chains. Now that will, what that will do is it will make the polymer more rigid, make it stronger. Okay, so if you imagine, I just draw it down here, if you've got 1 polymer chain there, 1 polymer chain there, not only intermolecular forces, but every now and again you've got actually a covalent linkage with our carbons here. Okay, so Every now and again you've got that. If you wanted to make more cross-linkage, more covalent cross-linkages, so you would make the polymer even stronger. Don't forget you could have ones coming off to another polymer here. You'd make it even stronger. How can you increase the number of cross-links? Well, the way you could do that is in your copolymer, you'd have more of your hexane dioic acid with the side chain. So you'd increase the proportion of this monomer here in this one here. So just, yeah, with that side chain on it. You'd have less of this one with no side chain on it and more of that one, and you're going to end up with more cross links. So that's just a flavor of some of the questions they've asked about polymers. Be able to spot from a polymer chain the monomers that it's made from. Know your examples that they've stated in the spec, which are: you need to know terylene, you need to know Kevlar, and you need to know 6,6 nylon, which are in the previous video, so I'm not going to draw them now. And then be aware of the biodegradability of polyamides and polyesters. A bit more biodegradable because you've got the polar bond there, so that means water can attack it, and that's about it really.